Welcome and thank you for joining the third session of this series titled Load Balancing Options in Azure, the Art of the Possible. My name is David O'Keefe and I'll be your host for today. This session is being recorded. If you do not wish to be recorded, please drop now and you can watch the recordings later at aka.ms/AZ networking sessions. During this session, we will share a link to collect your feedback. We have made changes to the series based on your feedback, so please continue to let us know what you enjoy and where we can improve. As a reminder, this is a three-part series, and today's session is the final session of Series 1. Agendas, FAQ, and feedback forms for the session, as well as recordings and additional materials can be located at aka.ms/AZ networking sessions. Here is the agenda for our event today. We will immediately jump in with Nahali to discuss load balancing in Azure. Next, we'll welcome back John from Checkpoint to present on the Azure Gateway Load Balancer. And we'll finish up with a deep dive session on Azure Front Door with Mark DeGroot. As a reminder, here's the core team developing the content, organizing, and producing these sessions. We have Nahali Niogi, a principal cloud solutions architect supporting Microsoft partners. Javier Elizondo, a senior cloud solutions architect supporting software and digital platform customers. Myself, David O'Keefe, a partner technology strategist. Sean Croucher, a senior consultant working with the UK public sector. Heather Z, a principal cloud solutions architect focusing on Azure security. And finally, Matthew Betts, a principal cloud solutions architect supporting financial services customers. We'd like to say a huge thank you to our moderators supporting us today. As a reminder, please leverage the Q&A panel throughout the session to ask your questions. Here are your presenters for today's sessions. The one and only Nahali Niogi from Microsoft, John Gao from Checkpoint, and Mark DeGroot from Microsoft. So without further ado, I'll pass it over to Nahali to kick us off. Nahali, please take it away.
Thank you, David. Let me share my screen here. All right. Hi, everyone. Thank you for joining and welcome. I just want to take a moment again to thank our presenters, John and Mark, for being available and our moderators for working behind the scenes to support this live event. So today we're going to talk about load balancing in Azure. When it comes to load balancing, Azure has a rich and a large portfolio of options. So by now you are familiar with these layers in Draw.io. So we're going to dive right in. On my screen, you are seeing a multi-region design that we've covered in depth in the previous sessions. So you see two regions, region A and region B, East US and West US. And if you haven't watched the recording, we have covered all of this in depth and the link is in the invite. So let's look at the web subnet layer over here. Here you see that I have 3 VMs in the East region and I have 3 VMs in the West region. For the purpose of this session, we will consider these red, green, and blue VMs and cyan, magenta, and yellow VMs as our application that we will load balance. So let's look at all the options. So here you see that we have 6 different load balancing options in Azure. At a high level, we divide them as regional versus global, layer 4 versus layer 7, DNS dependent versus IP anycast. So let's look at the placement of all of these options. So from a placement perspective, we have here we see regional load balancers. Here we see a global load balancer, and off to the side we have a gateway load balancer, slightly different use case, and we are going to go into a lot of depth with the gateway load balancer. So let me just point out all of the load balancers that we would be looking at. So there are two that are numbered as one, which are the internal load balancer and the external load balancer. They are both layer 4. And then we have the application gateway, which is layer 7. Of course, all of these are considered regional. And then we look at the global load balancer. We'll start with number 3, which is the cross-region load balancer. This is a newer one in our portfolio. Then we have the traffic manager, which is DNS-based, and then we have Azure Front Door. All of these, of course, are global load balancer. And then we will be covering, we'll be doing a deep dive on gateway load balancer use case as well. So with that, let's start looking at our first load balancer, which is the layer 4 load balancer. Of course, anytime you're looking at the screen, I will make sure that we have the top right-hand corner showing the exact load balancer that we are looking at. Now, there is a lot happening on the screen, so let's unpack the different items that I'm showing on the screen. First of all, there are two layer 4 load balancers over here, internal load balancer and an external load balancer. The internal load balancer would have an internal or a private IP, and the external one would have a public IP that's accessible from the internet. And then the important thing with all of these load balancers, it is what we can put in the backend pool. So here you could see that I have the red and the green VM in the backend pool, and I have a red dash line showing that in the backend pool, I cannot have anything that is across the express route in the data center, for example. In other words, your backends have to be in the same VNet where the load balancer is deployed, right? So that's an important item to consider. And from a configuration standpoint, I have put a screen capture, but if you have managed Citrix or an F5 or any load balancers, appliance-based or hardware-based load balancers, the classic items that you would configure are front-end IP, back-end IP, and session persistence. And that's what we offer as well. And from a session persistence perspective, the default persistence is 5 tuple, which gives us a much balanced distribution of the load if you are behind a NATed IP, for example. All right, so let's look at the different user flows. So this dotted lines are showing user flows. So there are two different types of users. One is an external user, this red user. That user can hit our external load balancer directly in both of these regions. All right, and then we have an internal user, the green user that is sitting either on a private connected branch. In this example, it's showing a data center, but it could be any privately connected branch that has routing to the Azure data center. So this user can directly access the internal load balancer. So now let's take a moment to understand the outbound flows. When we did the first session, I took a deep dive into different type of outbound options that are available in Azure. Now it becomes critical to bring this up in this session as well, because the external gateway also acts as an outbound, as an egress gateway for certain type of workload. So for example, if this VM is sitting behind the external load balancer, it can also egress through the external load balancer. I talked about a corner case about this internal load balancer. So for example, let's say that this 3 VMs, red, green, and blue, are behind the internal load balancer. And if they don't have any instance level public IP, they still need a NAT gateway or an external load balancer to egress. So that's an important point to keep in mind when you are using internal load balancer. So I will light up this option again. I want to, speaking of this external load balancer, to use that as an egress point, there is an important best practice consideration. So when you use that for an outbound SNAT, you may want to use a prefix list instead of a static IP. So I have called out a couple of best practices to keep in mind. Also, there is a possibility of you running into SNAT port exhaustion with this methodology. So we do recommend NAT gateway. But there is a very interesting metric that you can monitor. So you may want to turn on monitoring for that metric. With that, I'm going to talk about two very important concepts with load balancer, with layer 4 load balancer. One is the floating IP. So floating IP is used for SQL workload balancing, and its primary use is for port reuse. So I have taken this right out of the Azure documentation, and if you have this draw.io file and you click on it, it will take you to the exact documentation. But I want to take a moment to talk about floating IP and the use case for the floating IP. So when floating IP is enabled, notice how it says after floating IP. So when floating IP is enabled on the load balancer, it changes the IP scheme in such a way that when it sends packets to the downstream VMs, it keeps the front end IP, it keeps this VIP instead of the backend IP of the VM. So in other words, these VMs have to be listening for the VIP, the public front end IP of the load balancer. Now, this technique is used by default in Azure Kubernetes Services, so AKS. When you deploy an AKS cluster with a load balancer, floating IP is enabled by default. So that is the concept of floating IP. And then we have a concept of HA ports. HA ports, the use case for HA ports is with NVA high availability. So we're going to cover this in a lot of depth. We are going to cover this. Oops, let me just make sure I can see the screen. In the future session, I believe it's 2 sessions from now. But remember, we talked about the NVA high availability. There is this classic design called load balancer sandwich design, where you have 2 load balancers and NVA in the middle. That's when you want to use HA ports, where you want to load balance all of the ports and not just one port. So that's the use case for HA ports. And I want to call out one important point, that when you use the load balancer, layer 4 load balancer, it preserves the source IP. If I have time, I'm going to do a demo. If not, I do have a video on my YouTube channel that you can watch, but it will show you exactly how the source IP is preserved. If this user accesses this load balancer, this VM would see the source IP of this user. Right. So with that, we will go into our second load balancing option, which is the application gateway. So notice the number 2 over here, and we will be looking at the number 2 over here. So application gateway is a layer 7 load balancer. So it is typically used for web-based workload. The reason being, it gleans into the HTTP header, and it can do some intelligent routing decision based on the HTTP header. And we'll go into a lot of details of how the URL-based routing works. To begin with, let's look at all of the different backends that are possible. So if you see this blue dashed lines, that is showing you the different type of backends that are possible. So in addition to a VM-based backends, you can also route, as long as you can route to this blue VM across the express route or any kind of private connectivity, it can be placed in the backend pool. So again, as long as you have routing, it can be placed in the backend pool. Same goes here. You can see that I have the Cyan VM across the VNet peering behind the application gateway. And you could also have a cross-cloud public IP or even Azure PaaS services. So again, this is showing you an application gateway in the East region, and this one is the application gateway in the West region. Okay, again, this is still a regional construct. So there are a couple of best practices when it comes to application gateway. If you're going to be scaling and if you're going to be using the V2 version of the application gateway, it supports up to 125 instances. So you want to ensure that when you size your application gateway subnet, you size it correctly, depending on how much you're going to scale. If you're going to scale all the way up to 125 instances, and then you need 5 more for the reserved ones, you want to have a /24. Of course, there is an optional WAF component, web application firewall component that comes with the application gateway that you can turn on. And it offers a lot of features, right? So you could, I mentioned auto scaling. You can do URL-based routing, SSL offloading, end-to-end encryption as well. We'll deep dive into one of these features, which is the most common one that you would see, is the URL-based routing. So let's look at how that looks like from a user perspective. So imagine that this user is coming in and using this URL colors.nihalineyogi.org. It could be any domain name. So when it uses that URL, it can access this application gateway directly. Of course, with that same URL, if you just put a domain name / for example, red or /green or blue, and if you put the appropriate pool behind it, the same IP address can be used for different paths in the URL. And same thing goes with host-based routing. So you could have red.domain name, green.domain name, and blue.domain name, and you can have different pools behind it to direct it to the appropriate pool. So quite powerful URL-based routing. Of course, you want to make sure you have your CNAME records set up appropriately. So I've put an example of how this colors green and red CNAMEs are set up. So you could take a look at those as well. Now, another important thing with application gateway is that notice that you can have only one application gateway, and it can be used by internal user as well as the external user. The same application gateway can have a private and a public IP. Also, the session persistent method, application gateway does support the cookie-based session persistence. So, your user sessions can go to the same server. It's also called, sometimes it's referred to as sticky session support, used for shopping cart kind of applications. And lastly, there is a use case for application gateway can be used as an ingress controller, as an AGIC with Azure Kubernetes Services, AKS. So AGIC stands for Application Gateway as an Ingress Controller. There is a link to my blog. I've written a lot about AGIC and AKS, a very detailed blog. So if you want, there is a link to that blog as well. And again, if I have time, I will do a demo of how the XFF header gets written when you have application gateway, because application gateway is a layer 7 proxy, so it will not preserve the original source. All right, so we'll show that in a demo. If not, you could look it up on my YouTube video. So with that, let me just make sure that I have covered all of the important points here. One more item, you will see that in every load balancer, I keep a screen capture of what options do we have for backend tools, right? So IP, VM, app services. So be sure to check that out as well. And with that, I'm going to go into the third option, which is the cross-region load balancer. So cross-region load balancer is rather new, still in preview. It's still a preview feature, so I want to call that out. It is a global load balancer, and it has a concept of home region. So notice how my cross-region load balancer is in East US 2, while my the two load balancers that are behind the cross-region, this and this, they are in East US and West US. However, the cross-region load balancer is in East US 2. So there are certain regions that are available today as home regions. I have listed them over here, but it's important to know that you would need to deploy that in the home region. And then, of course, the backend can be, it has to be a standard public load balancer. The technology that it uses behind the scene is called IP Anycast, and the failover works really well. It actually directs the user to the closest endpoint, and it also preserves the client IP. All right. So let's go to option number 4. Option number 4 is Traffic Manager. We call it ATM, Azure Traffic Manager. There is a lot to see here. So the biggest thing to call out here is it is a global load balancer and a DNS-based load balancer. And from a backend perspective, if you see these dashed lines, all of these dashed lines is showing you the variety of backends that are possible. So you could essentially have a multi-cloud public IP. You could have a load balancer, an app gateway. You can also have something publicly available in your data center, an Azure PaaS service. So quite powerful. I also worked with a customer where we had, in fact, a Citrix, a third-party appliance that can also be behind the traffic manager. All right. Now I mentioned that it uses DNS, so it is very, very TTL dependent, the time to live for the DNS, and let's understand that a little bit more using with the user flows and why that is important. So let's say that this user, when the user accesses this domain tm trafficmanager.nihalineogi.org, what happens is behind the scene, the traffic manager uses DNS to redirect this client, depending on the routing method, either to this load balancer or to this load balancer. So it actually gives the appropriate endpoint, a DNS endpoint. So notice that Traffic Manager is not in the data path. It merely gives the endpoint, and then the data path is the green flow. So then the user goes directly to the east load balancer, if depending on the traffic method. The default, depending on the routing method. The default routing method is performance-based. So what performance-based routing method does is it directs you to the closest endpoint. And let's talk a little bit about the routing methods as well. So there's quite a few routing methods available over here. I have a screen capture just to kind of talk through some of the common ones. I'll talk about the priority one. The use case for the priority routing method is typically when you have a primary and a secondary, a failover type design. You want to use the priority routing method. So it always goes to the primary data center and only in the event of failure goes to the secondary one. And then you have the weighted one where you can distribute the traffic across a set of endpoints. Of course, if you put the same weight, it means equal distribution. So that talks about all of the important points. And I also put, an output of a dig command over here so you can take a look at how it's working end to end. With that, let me do a quick time check for myself here. And all right, so I'll go to the next layer and the next option, which is Azure Front Door. Mark, my colleague, is going to cover Front Door in depth. So I'll just touch upon a few points just for the completeness of this this session. But for Azure Front Door is again a global and operates at layer 7. So if you look at the backends, these dash lines again are the different possible backends that are available to Azure Front Door. And from a user flow perspective, the user gets a very good experience because it attaches to the closest edge location. We have 118 plus edge locations. So you can imagine the user experience that comes with that kind of Anycast based IP routing that it uses behind the scenes. And then there is a use case. You can see that I have these dashed lines showing the backend. We now also support private endpoints with Azure Front Door, and I have a blog written about this with AKS cluster and private endpoint using Front Door. So you could, it's also on my GitHub, so you could take a look at that as well. Now, Mark again is going to cover this in depth, so I will hold off for more on Front Door right here. So now let's get into the gateway load balancer. So what is the use case for the gateway load balancer? So over here, you can see that the gateway load balancer can be in its own VNet, in its own subscription and a different tenant. So that's where it can be deployed. But let's understand the use case for gateway load balancer. So remember, we talked about NBA high availability. The use case for gateway load balancer is that this design is quite complex. For north-south traffic, instead of having this design, we could use the gateway load balancer to load balance the appliances. In this case, I'm using the 2 Checkpoint CloudGuard appliances. So think of it as the way to think of this whole design is think of this as your protected workload. This is the workload you want to protect, like the consumer of the service. And then think of this as something that you're protecting it with. And the concept here is that this whole VNet is quite transparent to the user, right? So it's that service insertion, bump in the wire kind of concept. And let me demonstrate that with this flow so you could see what that means. So really, when the user comes in and kind of goes to your protected workload, it has no idea that this whole VNet exists, right? So it transparently gets redirected to these NVAs, and you can get the filtering and the advanced security capability of the NVA. So you might think, how does this work? So now I will say that we are going into level 500 of Azure networking to understand how this works. So again, behind the scenes, what it does is when you deploy these two NVAs, what it does is it establishes two VXLAN tunnels with the Azure load balancer. So if you remember, when you set up the gateway load balancer, it prompts you for two different ports, internal port and an external port. All right, so what that means is, let's say that the external port that you set up was 2001, and the internal port that you set up was 200. What that means is it sets up two VXLAN tunnel with UDP 2001 port and UDP 2000. And these two VXLAN, there are two VXLAN tunnels that get established. So notice now if I light up the inbound flow, notice that the user is at the source IP, and it has its own source IP, and the destination is this load balancer. Now, when the packets are sent to these NVAs, if you notice, I did a packet capture on these NVAs, and if you notice, the outer packet and the inner packet. The inner packet is quite secured. This original packet is untouched, and the outer packet is these two VTEP tunnel endpoints. All right, and that's how the traffic flows through it. So this the inner packet are untouched, and so you also notice that there are two VNIs that get set up, and those were also the one in the configs. And those VNIs are the VXLAN identifier, uniquely identifies the two tunnels, 800 and 8801. So again, I want to give a large shout out here to Checkpoint and John for helping me set up this lab so I can share this detailed packet captures and exactly the inner workings of the tunnels that get built behind the scenes. So thank you, John, for your help. Appreciate that. And then you can see this flow that I showed you is the inbound flow coming from the user to the protected workload. Similarly, we also have the outbound flow, and the outbound flow follows the same path, right? So it's that bump in the wire. And if you have worked with NSX and other technology, software-defined networking technologies, there is a concept of service insertion. So that's exactly what's going on with this whole VNet. And John's going to go into a lot of details about how that, and I won't steal his thunder, but how that experience looks like for an end user. So we'll wait for John to do his presentation as well. And then, if you're new to VXLAN, I have written as simple as a blog on VXLAN. Take a look at that. You can set it up with just using two Linux hosts, basically to demonstrate this whole encapsulation, inner packet, outer packet. So essentially doing layer 2 over layer 3. Now, two important considerations for this is today, we're not supporting this kind of chaining. In other words, having this load balancer chain with the gateway load balancer. We only support it with an instance level public IP and a standard load balancer, it is not supported with application gateway. And again, not south traffic only, we still need the NVA high availability design for the east-west traffic support. And lastly, I will say that we have a lot of variety of partners that are supported for the Great Gateway Subnet load balance for the gateway load balancer. With that, I am going to hand it over to you, John, and thank you everyone for listening.
Hi, Nahali. Thank you so much for that. Guys, give me a second. I'm going to share my screen. Okay, everyone. This is John, Cloud Alliance Architect from Checkpoint. Today, I'm going to give an overview of Checkpoint's integration with the Azure Gateway Load Balancer. On our agenda today, over the next few minutes, I'm going to start with an introduction to Gateway Load Balancer and a deep dive into the ingress and egress packet flows. I'm also going to go over some of our key use cases and end my session with how easy it is to deploy both the Gateway Load Balancer and the Cloud Network Security together. So as Nahali highlighted a few minutes ago, there are different options to provide ingress connectivity. And as you can see here, this is our current Cloud Network Security load balancer sandwich design, right? So this is the NVA sandwich design that Nahali mentioned earlier. This particular design provides options for high availability or VMSS, right? A scale set allowing our customers to scale in and scale out based on the traffic requirements. Now, in the same architecture applies for the web application firewalls, such as the Azure Gateway, such as the Azure Application Gateway, Checkpoint AppSec, which is our version of the RAF, and other Microsoft partners such as F5, Barracuda will also have similar, if not the same architecture. Now, a few considerations specifically for ingress connectivity with this design. First, we need to source NAT our traffic, right? As Nahali mentioned, you need to source NAT traffic to keep the traffic symmetry, which means that we'll have to source NAT all incoming traffic to our internal interface of our security gateway. So if you look at the packet coming in from the internet, it'll hit the floating IP, it'll hit the external load balancer, then the load balancer will make a decision where to send the next packet to, right? Because there are two different Checkpoint NVAs here. The gateway will send it to, let's say in this example, VM number 1. Now, after we inspect the traffic, if it's allowed, then we will send it directly into the application internal load balancer or another external load balancer. Now, the reply packet, however, will go to the internal load balancer. Again, because this sandwich design, the next hop IP address or default gateway is going to be the internal load balancer. So in this case, when the reply packet, right, the SYNAC packet comes back, it'll hit this internal load balancer. Now, because this internal load balancer never seen that the initial SYN packet, it doesn't know where to send it back to, right? So or where they originate from. So it could potentially send to VM2, and in this case, the VM number 2 or CloudGuard gateway here will drop that packet because it'll be asymmetrical routing, right? So because we never saw the initial SYN, we'll drop that packet. So that's why source natting is very important in this particular architecture. So just to keep the traffic symmetry. So once we NAT the incoming traffic here, we will send the traffic to the application. The application will then send it back to our internal interface. So that's the first consideration in terms of ingress for this particular design pattern. Our second consideration is because this is a hub and spoke design. Customers will need to peer the workload VNet to our security VNet here, right? So again, like what Nahali mentioned earlier, this creates a bit of complexity, right? Which means that customers will need to peer the VNet, and this will require a separate UDR. For larger environments with multiple VNets, customers can always leverage the Azure route server to help them manage the routes. Now, lastly, is to protect an existing application already in production, right? Customer will need to make an architectural change to this hub and spoke design, right, in order for Cloud Network Security to inspect the traffic. Now, the problem that we're trying to solve here is how do we protect our customers' external-facing applications with a simple network architecture that also provides availability and scalability? So the solution is to integrate Cloud Network Security with the Azure Gateway Load Balancer. With the Gateway Load Balancer, you can easily add or remove advanced threat prevention capabilities from CloudGuard without the extra management overhead. It provides that bump in the wire technology to ensure that all traffic to your external facing application is first secured by CloudGuard before the traffic arriving to your application. How it works is the gateway load balancer encapsulates the traffic using VXLAN, so there is no change to original traffic, and CloudGuard would decapsulate the packet and apply inspection. Now, as a result, CloudGuard is able to see the original source of the traffic, and also ensuring the source and destination function without any knowledge of having the gateway load balancer in path. Now, the first advantage of the gateway load balancer is there is no more source NAT for inbound connections, right? This will enable application owners to easily run things like data analytics to see demographic of the users without looking at the packet headers from the X484. Second is any existing application can be easily protected by CloudGuard Network Security without making a significant architectural change. So, for example, security administrators can now make CloudGuard easily consumable, right? This means that any application owner, right, in the same company or even not, right, have full control rather to redirect the application traffic to CloudGuard for inspection or not. This is also used for enhancing security for existing application without, again, making that architectural change. And for the customers that have multiple stakeholders, can easily consume security at their discretion. This is all possible because Gateway Load Balancer can support multiple external load balancers, can support cross-region, and different subscription support as well. Again, this is all possible without having to make any architectural changes. In terms of use cases, first and foremost, at least from my experience, Gateway Load Balancer is the easiest way to incorporate security to your external facing applications, right? Two reasons. Number one, it does not require a separate security network architecture, such as the hub and spoke network design I mentioned earlier. Second is the Gateway Load Balancer essentially gives me the on and off switch, right? So this makes the adoption of ingress protection and troubleshooting very easy, right? So just turn it off if something is not right, and to see if the application that goes through, to turn it on, right, to enhance your security for your external facing application. The other use case is SSL interception, where it is not a really good use case for compliance and security reasons. It gives CloudGuard and other Microsoft partners the ability to do deep packet inspection. You can't do that. You can't really do much without SSL interception in terms of packet inspection. You can also offload your SSL certificates to CloudGuard, so customers don't have to manage the individual certificates per the application workload. From an ingress perspective, IPS is a must, right? Checkpoint usually release our signatures within hours of new discovery of zero-day vulnerability. This will allow customers time to patch their servers while we're actually preventing these attacks from coming for attacking your workload and compromising your servers. Lastly, anti-bot is my personal favorite because it will stop the command and control, right, of infected workloads in your environment. It will also trigger that, hey, this workload is being compromised, and maybe it's time to isolate that workload and run some forensics and see what really happened to that workload. Why is it communicating out, right? So with that, I'm going to dive a little bit into the packet flow. So this is just our animation of how the packet flow, right? So packet from the internet, it hits the external load balancer. The SYN packet will then transfer to the gateway load balancer. And then gateway load balancer does a health check, right? Ensuring that the gateways are healthy before it sends the packet to the CloudGuard for inspection. Once we give the okay, right, this packet is okay to pass, then we'll give it back to the gateway load balancer, to the external load balancer, and then eventually make the SYN packet make its way to the workloads. Now the SYNAP packet will follow the same path. It'll go back to the external load balancer, to the gateway load balancer, and the SYNAP packet will go back to the original gateway that did the initial SYN packet inspection. And the reply packet will then get back to the original source. So that's the inbound connection. And this is the outbound scenario, right? So the workloads are also protected by CloudGuard as well for egress connectivity. So for egress, the SYN packet will go to external load balancer, gateway load balancer, the checkpoint here. And then once the packet is okay, then we'll redirect it back out to the internet. Okay, following the gateway load balancer to external load balancer, and then eventually the internet here. So that's pretty much the packet flow, right? Exactly the same as how Holly mentioned earlier in her design. Just this is a bit of an animation on how it all works. So I'm gonna spend the next minute or so on how to deploy the solution, right? So as Holly mentioned earlier, there are a lot of VXLAN configuration, right? So our deployment will take care of all that for our customer, including deploying the gateway load balancer. So to deploy our solution is currently in public preview. You can find it in the Azure Marketplace and search for CloudGuard. And under CloudGuard Network Security, click on Create. There's a public preview, CloudGuard Gateway Load Balancer. So once you click on that, it'll bring us to the page to fill in the information, right? So create the resource group, the region, the name of the scale set. Again, we're actually deploying this as a scale set. And then under the next tab, we'll have the number of initial gateways, right? So because we have the ability to scale out, and because of that, we created a way to automate onboarding of a security gateways to our management station, so make it even easier for our customers to manage these gateways. And in case there's a scale out event, these gateways will configure automatically with the exact same policy as the rest of the gateway fleet. One important feature here that I always miss is that you plan on managing these gateways via the external IP address. You need to assign it a public IP address. Okay. The rest of the tabs are very checkpoint specific. Select your version, select your first-time SIG key, and then lastly is the networking tab. So put it in the proper network there. This concludes my part of the presentation. So thank you very much, everyone. Thank you for inviting me. I'm going to pass this over to our next presenter, Mark. Thank you, everyone.
Okay, so good afternoon, everyone. I'm going to talk a little bit about I'm going to talk a little bit about application gateway and load balance, and Azure front door. So basically Azure load balancing for web application delivery. And just to put things a little bit into perspective, this is our portfolio of sort of application delivery services, and we've discussed a couple of them already. So Traffic Manager and Load Balancer have been discussed, and we sort of make this distinction into either global or regional, and then any protocol or HTTP, HTTPS, so web. And we're going to talk about the bottom half of the screen here, so front door and application gateway. And just a few words about CDN as well. So if you look at how these work, so application gateway is actually a regional application delivery controller in the sense that it is deployed in an Azure region in a virtual network. So it is tied to a virtual network. Azure Front Door, on the other hand, is not even a true Azure resource in the sense that it is not delivered out of our regional data centers. Azure Front Door, in fact, is delivered out of the nodes that we have on our network edges. So this service does not live in a data center at all. It lives in our network edge nodes. Now, when you create an application gateway, you give it a public IP address, right? You create a public IP in your subscription, and that public IP is then tied to the application gateway. Public IPs in Azure supports two methods of routing. One is Microsoft routing, and the other is called Internet routed. And the distinction is that with Microsoft routing, we do everything we can to get client traffic as quickly as we can on our network, whereas with Internet routing, we will try to leave the client traffic on the internet and only pull it into our network as close as possible to the destination. Now, it works a little bit different for Front Door. Front Door actually always publishes an Anycast address out of all of these edge nodes. So Front Door always publishes the same address out of all of these nodes. And for Front Door, we talk about an Anycast address. In fact, this is very similar to the Microsoft method of routing public IPs. And we'll talk about that in a minute. First, just a quick refresher on what Anycast is. Like I said, with Anycast, you basically publish the same IP address out of a whole number of nodes or ASs even. So if we have a quad 8 address here, and this client needs to send an IP a packet to a service that is published on this quad 8 address, it could go, go the shortest AS path to, where this IP address is published out into the internet. So this is 2 AS hops, and this is one further away. Now, if this dies, then internet routing will automatically make sure that, without the client even noticing, we go to the next best path to this quad 8 address, right? And this is exactly how it works with Azure Front Door Resilience. So, like I said, Azure Front Door exists in all of our edge nodes. So if this big cloud is our wide area network, the Microsoft wide area network, with a couple of Azure regions in there, the Azure regions both each run an origin for a web service that is published. We have the general internet here with clients and users. Normally, with this particular user, Anycast picks the closest POP on the network, and then within the network, from the edge nodes, from the front door edge nodes, we determine the fastest path to the backend. And should this backend, for some reason, no longer be available, front door automatically fails over to the next nearest backend within the Microsoft area, within the Microsoft wide area network. Now, should there be a failure on the internet, or should this hang on, let me go and get my laser pointer here. I want to do that. Should this node here fail, then BGP routing on the internet automatically fails the client over to the next nearest node, right? This is how, the Anycast routing works, as I've just described. Now, with application gateway, suppose we have an Azure region where we've deployed application gateway, or a couple of instances of application gateway, and we've given our application gateway instance an IP address with internet routing. Then what happens is this client that sits all the way over here needs to get to this instance of application gateway. And because this public IP is only published out of this edge node, because that edge node is the closest to the region where application gateway is deployed, their traffic travels the internet. So it goes from AS to AS, hops, 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 and then it enters our network. Compare that to when the public IP of this application gateway instance is set for Microsoft routing, then we essentially publish the same IP, or advertise, I should say, the same IP address out of all of our network edges, and the client enters the Microsoft network as quickly as possible. Now, this kind of Microsoft routing method for public IPs is, in fact, you will notice, exactly the same as the Anycast address that front door uses. So the question then arises, what is front door good for? Could we not just suffice with application gateway and public IPs with Microsoft routing? Well, that's the next step here. What will we do? Is application gateway, or does front door add any value over application gateway? And the answer to that is yes, it certainly does. Because if you run application gateway in an Azure region, obviously your public IP will be set for Microsoft routing and your IP address will be published out of all of the edges. But that still, you enter the Microsoft network and you're still at layer 4. Nothing happens really with the traffic. It travels all the way across the Microsoft network. Of course, it's a first-class network, but we can't make the world any smaller. So you still have your long network path there. Compare that to Azure Front Door. Azure Front Door is not just an entry point into the network. Azure Front Door is actually an application delivery controller that sits on the edges of our network. So the actual application delivery controller sits closest to the end user. And this brings all sorts of advantages. It essentially means that we can do application acceleration from the edge to the Azure region where the origin sits. And one important way, or one way that Azure Front Door does that is through a method called split TCP. So essentially what we do is we have a user hitting a network over a short path. So this is a new TCP. This is a new TCP HTTPS connection that is set up by the user. And this is fairly quick because this distance or this latency here is fairly small. the largest latency to the origin, the longest path to the origin, the longest part of the path to the origin is within our network. And what we will do there is we will try to reuse existing connections between Azure Front Door and the origin. So we avoid having to set up new TCP, HTTPS connections for every new request. We just keep the connection alive, and if a new request arrives, we reuse the existing connection. And the result is a very significant improvement of the total user to backend latency that the user experiences. Obviously, we don't make the world any smaller, but because for the long stretch, the long haul here, we do not set up new connections every time we see a request. We avoid that long haul, back and forth. HTTPS, as we'll explain, includes 7 back and forths. And we just don't have to do those because we already use that connection. So how does that work? So some maths here. Suppose we have a user on the Microsoft campus in Redmond, and we have a backend in US Central in Chicago. So there is a one-way path of 35 milliseconds, and suppose this is application gateway sits here, the user sits here. This is a cold connection, so we still need to set up the connection. Versus we have the same user on the Microsoft campus, the backend still in US Central in Chicago, but we have a pre-existing connection between the instance of Front Door in the edge node in Seattle and the backend in US Central. So why would there be an existing connection? Well, this would be because we have already served a request to this particular backend. If some other user has hit it and we've set up that connection for that user, no longer needed. We don't just immediately hang up the phone. We'll keep the connection alive. Now then, this new user comes in, and the only thing this new user has to do is establish a connection over the short hop from Redmond to the Seattle edge, which is only 5 milliseconds one way, right? So let's see how that works out when we start the connection. So we go directly to the app. We have 35 milliseconds one way. So first we do our SYN, 35 milliseconds. We do our ACK, another 35 milliseconds. We combine this, we do a SYN, we do a SYN ACK, and then our ACK we combine with the HTTPS client hello, another 35 milliseconds. We do the HTTPS setup, and eventually after 245 milliseconds, we're ready to basically receive the first byte of application data. Now compare that to the situation where we go via Front Door and we only have 5 milliseconds single way. That means that only after 35 milliseconds, we're already ready to receive the first byte of application data. So we save over 200 milliseconds of data just setting up the request, just starting the request, setting up the connection. Now, if we then expand that, and if we look at some of the parameters here, we assume that, Front Door serving an HTTPS or HTTP, it takes 2 milliseconds here. The app takes 100 milliseconds to send all this data, time to last byte. So if we add those numbers in, then we see that we go directly from Seattle to the app in Chicago. We have a request start of 245 milliseconds. Now, obviously, we don't have Front Door in the path, so Front Door here does not add any data. We have the 100 milliseconds the app adds. And then we have the 35 milliseconds app to client traffic. So in total, it takes us 380 milliseconds to receive the data from the application. Compare that if we go via Front Door, we save a considerable amount of time by just using only the setting up the cold connection over the shortest hop, and we reuse the long hop. Obviously, Front Door adds 2 milliseconds, then Front Door needs to go to the backend over the hot connection, which takes 30 milliseconds. The app adds 100, the data comes back from the app, another 30 milliseconds. Front Door adds 2 milliseconds here, and we have another 5 milliseconds for Front Door to client, and we have about 200 milliseconds, 204 milliseconds. So we save a very large, about 50%, 45% of the total time we save there. Now, if you make that global and the distance is the long part of the distance gets longer and longer because we have all these edges around the world. We're always very close to the user with front door. You can see that, we save or we speed up the longer the long haul is, so the longer the distance is between the front door edge and where the application sits in Azure, the more time we save there. Front door adds a few other things here. So there's some caching and compression that is added on the edge that also improves the speed of delivery. We fetch and cache large files using object chunking if the backend supports this, which basically means that while we serve one chunk to the client, we start prefetching the other chunk, the next chunk from the origin. And front door has dynamic compression capabilities as well. So a little bit of a demo. This is not a live demo. This is something I did earlier, just to see how that works. So we have a web app located in the central US. It serves a 100 kilobyte GIF file over HTTPS, and we do that 50 times, either directly from the web app or via front door. Our client was located near Amsterdam, and the round trip to the cold path, the long path round trip to the web app was 120 milliseconds, and the round trip from the location of the client to the nearest edge was 20 milliseconds. And you will see on the next screen that the AFD reduces the total file load time from approximately 800 to 400 milliseconds. If I have a look at this, you can see that this is the little script that loads that content from this origin, and you can see it takes about 800 milliseconds to load. If you go through front door, you can see it takes only 400 milliseconds. So this is where front door really adds a lot of value over just going with application gateway in a region. Okay, this was the actual latency we measured from the client to the origin, or from the client to the nearest edge. So we spoke a lot about dynamic application acceleration. So what about serving static content, right? And the CDN product? Well, content delivery of static content is still very, very important, and we still do that. We used to have two separate products for this. So we used to have Azure Front Door just to do the dynamic application acceleration, and then a separate product called Azure CDN. These two have now been merged into the new Azure Front Door Standard and Premium SKUs, and you don't no longer need to set up, Azure CDN as a separate service and create separate CDN endpoints. This just happens when you create a front door, or you create a route in front door and you tick enable caching. Then front door automatically starts caching static content for you. The classic CDN still does exist as a product, and as you are probably aware, we had three kind of products within that service. We would have our own product delivered out of our edges, and we resell Akamai and Verizon. The idea is that you can easily get these two third-party products as Azure services without having to contract these services directly. You just spin up a CDN endpoint and you select which provider you want to use. Obviously, there are differences between these services, and you can see that we have the Azure CDN from Microsoft has its POPs in our global WAN. Verizon has POPs with large internet service providers, or with large internet exchanges, and Akamai is well known for having very, very large number of POPs with ISPs. So these are smaller POPs, but they are very close to the end users, which basically means that if you need more POPs, then you drift towards Akamai. Otherwise, we are more optimized for CDN to origin latency, and this is more optimized for client to CDN. There are also other considerations, especially with Verizon, who have optimization for video and media content that we at this point do not have yet. So last slide is a few words about the roadmap for Front Door. So we keep evolving the product. A large update over the past year was our SKUs. It says here public preview, but the new SKUs are now generally available. Some other things that are in the pipeline or are in fact in preview is mutual TLS. This is an important one. And then the next leap we will take is we will start to support HTTP 3 and TLS 1.3 as an important one, and a bunch of other features coming along down the pipeline. So I'm a few minutes over. So David, with that, I'm going to hand it back to you.
Sounds great. Thanks, Mark. I'd like to thank everyone today for their time attending this session. Please take a moment to fill out the feedback form that was posted as an announcement in chat. It helps us understand what you enjoyed and where we can continue to improve. And as always, please remember to visit aka.ms/AZ networking sessions for the content covered today. Thank you all.